Hello, everybody. So I have 10 slides, and this is a very big topic. And I'm aware many of you have different expertise areas, I imagine, in ICT sustainability. So I've written this proposal as possibly a general approach, but also taking a specific slice of ICT, in this case, deep learning systems. However, what I'm talking about today also extends in a broader picture in terms of ICT in general. So a few things I want to before I go into the presentation. One is the ICT footprint is very large in operation. So there are predictions and forecasts that ICT consumes between 8 to 11% of the world electricity usage. And that's been forecasted maybe to increase up to like 15, 20, 25, even some extreme cases 40% in a few decades. And that's driving agricultural sectors of emissions as well. So it's a really big consumption footprint. So ICT is heralded as the panacea to, okay, we can replace traditional industries, reducing the footprint, but now we have more ICT, increase from that. And the second thing I want to keep in your mind is one of the motivations for sustainable computing isn't just looking at efficiency. So I've been very privileged and spent some time at Google and Alibaba in China and the US. And specifically for one of these companies, I won't name who, I built them a system that reduced their footprint by 30%. And it translated to like $30 million worth of savings. So I was really happy about this. And they used that money to build another data center, another system from there. So actually it doubled the footprint. So I was thinking, what's the point of my work from that? So with that in mind, two things as we go into this presentation. First one is ICT footprint is huge. There are YouTube videos that consume more power than most countries in the world. That's something to keep in mind. I think Baby Shark consumes more power than Burundi for an entire year. Shocking thing. And the second is that if you do make savings, you might actually have some pain point increasing from it. And this topic is about deep learning systems. I picked deep learning systems for two reasons. One, it's a very new type of system that's kind of manifested in the last few years, and it's become very, very important in the next few decades from that. And it's a very big emitter, a big consumer from that. And also just as this is the wizard academic in me, that a lot of people use the word AI, machine learning, and deep learning interchangeably, and they're very different things. So I really want to give a little bit of actually what the thing actually is and why it's so interesting. So very quickly, deep learning is a subset of machine learning methods from that and concerned with neural networks. Okay? And these are roughly modeled on the neurons you find in human animal brains from. And more specifically, it's based on vector mathematics probability theory. So using multiplication, addition, tensorization, multiplication to actually operate from that. And deep neural networks are neural networks of three layers. So you see in the bottom left here, on the bottom left-hand side, we have a simple neural network. You have an input layer, some layers of weights and numbers, gives me an output. A deep neural network is you have multiple hidden layers from it. And in the last few years, we've seen lots of media and lots of research exploiting deep neural networks, for lots of different things: object detection, classification, audio detection, lots of different industries. So a bit more information. These are virtual constructs representing learned information. And these are very roughly equivalent to brain regions. Okay? They specialize currently in one or very few tasks. So like I said, you can train a deep learning model for image recognition, audio recognition from there, for recommendation systems from there. And these seems all very nice from there, but you think about it empirically, you have some software that you add addition, multiplication, transformations, executing on a hardware device. It runs on some machine from there. CPU, GPU, ASIC, FPGA, different type of devices. At the end of the day, they go to execute, have a power draw on the system. And there's lots of different types of deep learning models. They vary in the size, complexity, how many operations they can perform, accuracy determines how good the model is, how much computation, memory footprint, consumption. So lots of different models, all very different, but have different characteristics. But at the end of the day, they all have to run on a machine somewhere. So it brings me on to the topic of sustainability. So increasingly, many of us think about deep learning in terms of I buy a GPU, you can get a hold of one nowadays, and I run my model to train it and use it to my own machine. But more commonly, think of the large tech companies that host cloud services. So think of Microsoft, Google, Amazon. They have data centers, which are like power plants for computing, and they have hundreds or maybe thousands of different devices like GPUs in a single location. So if you want high quality compute as a service, you need high power compute infrastructure. Okay? So I kind of say, one of my students says to me, I was very apt, actually, you think about a data center for GPUs and even CPUs, it is a building filled with very extremely expensive hairdryers or complex ones. Technically, you could argue the usefulness, but most power, electricity draw from the grid into a computer is output into heat with some bit of light from it. And most of these, it's just making heat from them, heat cooling from them. So this in the bottom left is a Tesla card for a GPU, and 1,000 of these together is the equivalent power draw of a medium-sized town in a lot of places in Europe. So really big consumers from that. And there's always a continuous improvement in energy efficiency in machine learning. What I mean by this is that we can improve the efficiency of the compiling, the software, the operation, the middleware, the hardware power draw, the heat rejection, the cooling, the networking. We're trying to make these more efficient to reduce the overall consumption or energy outputs, the equivalent performance from them. However, at scale, there are problems. For this in the data industry, we know that the bigger things get, harder they are to do so. So most machine learning and deep learning services are hosted in facilities that have hundreds of these devices, and they're very expensive and huge power draw. So I want to highlight really 3 challenges about sustainable deep learning systems. And again, you can also apply this to other parts of computer science. So in AI specifically, there is a mentality of a rat race. Okay? So the 2 things machine people care about, as a general sense, is they want to make their models more accurate, because accuracy is good. The more accurate the model, the faster it is. And how general is the model itself, which means, can I apply it to different sets of animals than originally, kind of different sets of images you've seen before? So saying something like, my model is 0.6% more accurate at finding cats is a huge improvement, okay? Especially when you are 98%, 97%, 90% from there. Also, we recognize some dogs. So the problem with this approach is that it really has a leaderboard mentality to buy results. So increasingly, to get improvements of your accuracy and generalizability, you need more time to train to make the model learn from that. And that requires more time in a computer, but many more computers at the same time to be useful for it. So the example I give you here is AlphaGo. A couple of years ago, it was in the news that the AlphaGo model beats a grandmaster in Go. If you actually look at the behind the scenes of what it took to do so, there's about 1,000 hours of training on 5,000 devices, so computers from it. It's 200,000 kilowatt hours and 40 tons of CO2, 8,000 miles of vehicle miles, to just beat the best player. Now, you could argue that is a good use of time in terms of, 1,000 hours and 5,000 devices to beat the best player. Good trade-off, but you might say, okay, it's a nice thought experiment, but there'll be other scenarios that actually I spend 1,000 hours on this and I don't use this model again, or it's used for something that maybe not maybe the best case from them. And this is increasing from that. So increasingly, this idea of buying results really stampedes the idea of increased consumption. We need more power, more training, more energy to make this increase from that, which itself, I think, has some problems because, AlphaGo, it's a nice thought experiment, but think we did this for every single exercise from this. It's getting really expensive. Also, there's a degree of inequality in terms of some of this research can only be done by very large, expensive tech companies and not researchers, and that's a big problem as well, which I will allude to in some of the presentation. So the first one is about, there's an AI rat race, okay? Constant improvement, and that is increasing, massively accelerating the consumption of the resources. The second one, which is the one I'm very keen on for my project few years, is this idea of gratuitous ability. So more energy does not mean better deep learning models, okay? AKA, just because I throw more energy at a problem does not mean I'm going to get an improvement. It's the word feed me, see more. So if you have a poor model design, I make a really poor model for training, I could throw 1,000,000 hours at this model, it's never going to give me any improvements in accuracy. And the problem with training is that it's very, very hard to know if your training is going to be useful until it's finished. Okay? It might converge suddenly at the end from it. You let it run. That's a problem because also it encourages you to keep rerunning the model. So I make the model, I tweak it a bit, I run it again, I tweak it. So actually, it's not just the final training, it's the entire training itself from that. It's really expensive. And there was a paper from Facebook a couple of years ago. They had a massive natural language processing model, and they said in the paper, do not run this model. Too expensive from there. So think about it for a second. As a researcher, they're saying to us, do not run this model. Don't reproduce the work from it. It's not worth it. Okay? So these problems are consuming, powder of towns from it, and doing research at that scale is really expensive. And the real big problem is that it's difficult to determine the resource model benefit trade-off. I'll talk a little bit at the end actually what that should mean is that the vision should be, if I throw lots of energy on a deep learning, I should expect a smart model, a model that's really sophisticated. However, if I give it little amount of energy or power, I should expect a model that is much more scoped. Okay? And currently there's a massive mismatch in the area. In systems and machine learning, we don't really know the amount of resource that problem makes it actually work from that. And this isn't just deep learning training. There are other parts of the life cycle. So optimization means you try to make the model fit on a piece of hardware. That takes 6 to 10 hours per unique model and per device. So there are many different devices. So I'll take ARM as an example. ARM have a set of different architectures. And for one model, I need to optimize for every single device. If I change that model slightly by one parameter, do it again. So even though training as a one-off is a huge block of emissions, electricity consumption, optimization has to be done for every single change and perturbation. That is a huge amount to think about. Deployment, actually run the model. I think Facebook reported 2 trillion inferences in Facebook in a month, for example. So actually, even though the actual models run a few milliseconds, you've got a few trillion of them. That actually adds up over time as well. And the third thing that maybe someone will be familiar with is the idea of JEVON'S paradox, the rebound effect. So William JEVON was a British economist back in the British Revolution, and he argued that when you have technological or government progress or government policy to increase efficiency, you don't reduce consumption, you increase consumption. The example would be, I have a busy road outside. The intention is, okay, I should build another lane to make traffic flow better, but by doing so, I have now more cars, I have more pollution. And ICT in general was a great example of this. So when we were young, depends how people might be, a large amount of data might have been kilobytes or megabytes or maybe gigabytes, some people on the call from it. But that's just, nowadays that's very, very small. Terabytes and petabytes is now much, much larger. Because we've made improved efficiency, we can now do more storage, we can do more computation, we can transmit more network data from there. And also faster computes, more transistors. So actually, if you look at the overall consumption, each device is more efficient, but it accelerates consumption. Hence, you look at the consumption of ICT in the last 20 years, it's kind of exploded from it. And the problem is a lot of our efforts as system researchers and engineers accelerate this process. Okay? And the problem I have with this is that as a researcher, I say, hey, my work for efficiency makes actually the overconsumption increase. Now more data centers. I talk to government and they say, oh, talk to companies, they want to do this. Companies say, well, talk to researchers, they should be doing this. I talk to professors and they say, that's not my remit. That's the same difference you care about from it. So you have a three-way standoff actually who's responsible from this. And I call it labels the efficiency death march, which means everyone's so focused on their own small remits about improvements of GDP, improvements of efficiency, and actually the consumption keeps going up from that. And that's maybe a natural byproduct of our current environment of the markets, but actually, if you care about reducing overall footprint, just increase efficiency alone is not enough from that. That's a really, really big problem. So I'm going to leave you on this slide here is that I have 2 ideas, maybe people want to talk more about, as how to address this. So I think one thing going forward with computing systems is that we need power proportional systems. And I mean that in a very meaningful way, not kind of in a general sense. So if you think about it, a computer needs electricity for a power draw over your hardware and your device to actually run from it, okay? And there'd be a minimal power draw to function, okay? So the idea I have is that if I can give a machine 1 watt, it should do 1 watt's worth of work. If I get 1,000 watts, it should do 1,000 watts worth of work. And the question is, how do you build a device that will do both? Because obviously, people who do microprocessors can run on very 5, 6, 7 watts. They can't run to 1,000 watts, but actually think about it would be really interesting from that. And in terms of deep learning, the idea would be, okay, if I have a deep learning system exposed to very little amount of power, I should expect the entire system, from the operating system, the hardware, the system, to degrade gracefully to the bare minimum automatically, okay, in a very meaningful way. So suddenly, if it goes up, the thing kind of grows to life like a biological system from it. So it's got directly linking energy availability to the deep learning lifecycle. So today, you probably see my face, it's a sunny day and windy. I should expect all my infrastructure to actually flourish and work really well from it. But if it's dark, if it's windy, or there's no wind, I should expect perhaps my system should try to reconfigure itself to have a very, very low power state. Obviously, people will do this already, but there are limitations in current how software is built, but also our hardware has limitations from there as well. And the second thing I want to end on is characterizing energy usage of deep learning itself. So I allude to the idea that a smart model should have more energy, and a model that's slow maybe not. So given these 4 pictures of different biological creatures in general, so you could argue that a plant and the C. elegans, the worm here, has a very, very low energy usage. Okay, these are much simpler orders of life from there. Okay, they do less cognitive functions. A fruit fly, they're more complicated. They use a bit more energy. A dog on a surfboard, much smarter than me, for example, from there. It uses much more energy from that. And even humans, yeah. So humans, you can argue, we actually use quite a lot of energy compared to other creatures. Okay, there's in the biological sciences, when you look at evolutionary science from that, typically systems that can effectively use more energy are basically more cognitive from it. They have more activity. And in currently machine learning or deep learning, there's no idea of this. It's all connected. So the idea of saying, okay, I want a smart model. The smart model must be directly linked to, this would be a very energy intensive model for training and usage. But also you can have big and small, or maybe even cunning. Cunning might mean, okay, can you characterize a deep learning model and say, I'm going to run this thing? And it kind of surprises you. It's a very different way of characterizing machine learning, deep learning, because currently it's very hard to define, okay, it has an accuracy number. Maybe better language can be really good from that. So that's kind of how I leave from that. But obviously, a lot of these problems of efficiency, increased growth, power proportionality, these apply to a part of ICT. But given deep learning is kind of coming up the next decade or so, and maybe companies on the call might be interested, these are serious to think about. And with that, I thank you for your time.